The atoms of the various species involved in the reactants and product must be equal in number. Balance the number of oxygen and hydrogen atoms on both the sides of the reaction by adding water molecules to the required side. And also balance the number of atoms other than the oxygen and hydrogen. That's what I said. Oxidation has to be multiplied by 1 and reduction should be multiplied by 2. Hello dear students, I am Roja, your chemistry lecturer from Vidhyaashram PU College, the Temple of Excellence, Mysuru. So today we are going to continue the chapter Redox reactions. So in the previous session we have learnt about redox reactions and its importance, redox reaction in terms of electron transfer, then competitive electron transfer during redox reaction and oxidation number as well as types of redox reactions. In this session, we are going to study about balancing of redox equations, redox titration, that is indicators and endpoints, redox reactions and electrode processes, also about electrode potential. So let us start with how to balance redox equations. So every chemical equation must be balanced according to law of conservation of mass, that is the atoms of the various species involved in the reactants and product must be equal in number. The chemical equations which involve oxidation and reduction can be balanced by two methods. One is oxidation number method and the other one is ion electron method or half reaction method. But for now we will have to study about oxidation number method. A redox reaction can be balanced by using certain rules. So these are the rules to be followed. The first thing is write the given skeletal ionic equation of the reaction. Second thing is calculate the oxidation number of each atom in the reaction. Then identify the species that is undergoing oxidation and the species which is undergoing reduction process. Find the number of electrons involved in oxidation and reduction reaction and make them equal by multiplying with suitable number, and also balance the atoms other than oxygen and hydrogen. Then next step is balance the charges on both the sides of the reaction by adding H plus ions in acidic medium and OH minus ions in basic medium to the required side of the reaction. Balance the number of oxygen and hydrogen atoms on both the sides of the reaction by adding water molecules to the required side. So let us see with an example how to balance using the oxidation number method. Now let us study with an example how to balance the redox reaction. So here we have taken an example of copper reacting with nitrate ion gives copper ion plus nitric oxide. So the step 1 is write the ionic equation, that is copper reacting with nitrate ion gives copper ion plus nitric oxide. The second step is calculate oxidation state and each atom in the reaction. So copper here is an elemental state, so the oxidation state will be 0. In nitrate, N carries plus 5 oxidation number and oxygen carries minus 2 oxidation number. So when it reacts, it gives out copper ion, that is plus 2, and nitric oxide having nitrogen plus 4 and oxygen minus 2. The third step involves identify the oxidant and reductant in the reaction. So here copper undergoes oxidation state, that means it is going to lose electrons to form Cu2 plus ion. So the oxidation number increases from 0 to plus 2. Here in the next element, that is from nitric oxide, there is a reduction process, that is gaining of electrons. Therefore, the oxidation state of nitrogen here is plus 1. So here what we have to understand is copper on oxidation it loses 2 electrons, but on reduction it gains only 1 electron. So we have to balance the number. So we have to multiply the number in such a way that both the numbers should be same. The next step is balance the number of electrons involved in both oxidation and reduction reaction by multiplying oxidation reaction with 1 and reduction reaction with 2. And also balance the number of atoms other than the oxygen and hydrogen. That's what I said. Oxidation has to be multiplied by 1 and reduction should be multiplied by 2. And apart from balancing that number, we have to balance the atoms other than the oxygen and hydrogen. So that is the reaction. Next step involves now balance the charge on both the sides by adding 4H plus ion on reactant side. Why do we have to add 4H plus ions? It is in an acidic medium. That is why the reaction becomes Cu plus 2 NO3 minus plus 4H plus gives out Cu 2 plus charge plus 2 NO2. So here these 2 and 2 here represents balancing of the equation. And now next step is you have to balance the charges. So copper on an elemental state it is 0, nitrate it is minus 2 because only one charge multiplied by 2. Now proton has got 4, so it is 4. On the product side copper has got 2 plus charge, it is plus 2, and on the nitric oxide it's a combined form, so it is 0. Now on equating both the sides we get plus 2 is equal to plus 2. So both the sides, the charges on both the sides are equal. Now next step is balance hydrogen and oxygen atoms by adding water molecules to the product side. It is only to add it on the product side to have a balanced equation. So the reaction is Cu plus 2NO3 minus plus 4H plus ions gives copper 2 plus ion, then 2 nitric oxide plus 2 water molecules. So this gives the balanced redox reaction. Now let us understand redox titrations, their indicators and their endpoints. So just like acid-base titration use pH indicators, in redox titrations we use redox sensitive indicators, or sometimes the reactant itself acts as an indicator. So there are many cases that we come across during redox titrations. So in case 1, the reactant will be of a self-indicator, example potassium permanganate. Using potassium permanganate during redox titration, let us see how the endpoint is being found. In some titrations, the oxidizing and reducing agent is strongly colored. Example potassium permanganate. Here permanganate ion, that is MnO4 minus, it's of purple color, acts as both oxidant as well as self-indicator. As long as reductant, that is ferric ion or oxalate ion is present, permanganate ion gets reduced and the solution becomes colorless. As soon as all the reductant is consumed, the first permanganate pink color appears due to excess of permanganate ion. Sensitivity is even at 10 to the power minus 6 molarity of permanganate ion, color is visible so that it prevents overshooting, that pale pink color will be visible. The endpoint, what is the indicating point is appearance of permanent pale pink color will be the endpoint. So the second case is external indicator, that is example is potassium dichromate titration with diphenylamine. Some oxidants are not self-indicators like dichromate ion, which is of orange in color. Here a special redox indicator is added, that is diphenylamine. At equivalence point, excess oxidant oxidizes the indicator, sudden color changes, that is it gives an intense blue color, and therefore the endpoint is appearance of blue color of oxidized indicator. So here the indicator used is diphenylamine. Now let us see the case 3, that is iodometric titration. Here the starch is used as an indicator. Some oxidants can liberate iodine from iodide. For example, reaction between copper and iodide. Copper ion with iodide ion gives C2I2 plus I2 iodine. Iodine itself is colored but made intensely blue by adding starch indicator for the formation of starch iodine complex. So the liberated iodine is then titrated with sodium thiosulfate. So iodine, this is thiosulfate ion. Reacting, it gives iodide ion along with that tetrathionate anion. As soon as iodine is consumed, the blue color disappears and therefore end point is disappearance of blue color. So that gives the result. So let us see what is redox reactions and electrode processes. The oxidation and reduction half reaction may proceed indirectly in separate beakers known as half cells by passing an electricity. The device used for carrying out indirect redox reactions are called electrochemical cell. Therefore, electrochemical cell can be defined as a device in which the redox reaction is carried indirectly and the decrease in energy appears as the electrical energy. Example can be given as galvanic cell or Daniell cell. Now let us understand the working of electrochemical cell. So first thing is, take 1 molar concentrated aqueous solution of zinc sulfate and copper sulfate in 2 glass beakers. So there are 2 glass beakers, one with copper sulfate solution is of blue in color and one more is zinc sulfate is in the another beaker. Next, place a zinc rod in zinc sulfate solution while copper rod in copper sulfate solution. So these are the rods, this is zinc rod and that one is a copper rod placed in zinc sulfate and copper sulfate respectively. These metal rods are called as electrodes that connect the 2 electrodes with copper wire through a galvanometer. Connect the electrolytes in these 2 beakers through a salt bridge. These 2 electrodes should be connected using a galvanometer and there should also be a salt bridge connecting the solutions. Normally, potassium nitrate and potassium chloride acts as salts in the salt bridge since they have same ionic mobility of cations as well as anions. The 2 ends are packed with cotton plug. So that is how the experimental setup goes with. So what are the observations that can be done during this process is, the beaker placed on the left hand side is called oxidation half cell. Here zinc rod get oxidized to Zn2 plus ion. So that is what? It loses electrons, so it possesses 2 plus charge. The beaker placed on the right hand side is called reduction half cell, wherein copper ions of copper sulfate gets reduced to copper. That means it is gaining electrons towards itself, so it possesses copper. So next one is electrode potential. Electrode potential is defined as the potential difference between the electrode and its ions in solution. The electrode potential is generally measured under standard temperatures and pressure. That is, temperature used here is 298 Kelvin and for 1 molar concentration of ions in solution and is called as standard electrode potential and it is denoted by E0. So that is electrode potential. So this was about redox reactions. I hope you have understood. Thank you.